So hi there, welcome to this session. Today we shall be discussing about partial differential equation. And now let's just start. Today we shall be discussing of the Sobolev spaces, and let's start with our basic Hilbert Holder spaces. So without wasting time, let's just start. Sobolev spaces, Holder spaces are part of Sobolev space is a very important criteria and very important space in say set in PDE. The modern analysis of PDE requires dealing with the Sobolev space. Probably one lecture won't be sufficient for it, and I should arrange a few others. This would help in the establishment of the elliptic equation, solving the elliptic equation, the second order elliptic equation, and linear evolution equation, and many others. This is the very important, one of the most important criteria, and an important is going to be an important lecture. So please try to understand it correctly. Let us first deploy. This is a simple version of kind of Sobolev space, and this is a simple space, a holder space. So, what is a holder space? For holder space, assume U is. Let's start with the definition. U V U to R is bounded. Since it is a real valued function, it can be bounded and continuous. Continuous is defined from the elementary calculus. It's a basically Rn to U is a open subset of Rn. U is a, let me just write it. U is a open subset of Rn. So it's an Rn to basically subset of Rn to R function. So the concept of matrix space is used in the continuity definition. Now this is continuous, and we write U. We write U defined as the supremum. This is simply merely a notation, and it is the definition of this notation. Supremum of Ux, x belongs to U. So this is a notation of the of our. This is the notation, and this is the definition. X belongs to U. For all Ux, supremum of such a basically the modulus of this absolute value of this function, the modulus of this function. Basically, it is Ux is a real valued function, so this one is a real number whether minus or plus. So it we shall take only the positive. So it is the absolute value function, and so we are taking the supremum of U. The gamma Hilbert's this is the definition one. Now the gamma holder seminorm. The idea of norm is very important. In it's usually studied in the elementary courses of real analysis, and one should be familiar with this at this point of time. By this point of time, in my previous lectures, I probably have discussed this norm concept, and this is a semi-norm. In mathematics, we usually like to play with this languages to keep it simple and make it more intuitive, so that we can be mathematician can remember it. So this is a semi-norm, kind of why it is called. Let us see. U C 0 comma gamma U bar equal to supremum x comma y belongs to U, x equals to y, ux uy, this absolute value again, x minus y to the power gamma. This is where gamma is used. This is where gamma is used, and so it is. And the gamma holder norm. This is a holder seminorm in the gamma holder norm. Let's write it here. Gamma holder norm. Again U bar. U bar is nothing but it is the closure of U, basically. Is defined to be. This is a notation for definition, and this is defined to be mod of U. This norm is with respect to this is the continuous space. This usual notation plus notice it is the seminorm. It is again the holder space gamma holder seminorm. So this is the definition of the gamma holder norm. Now once we have done with this, let us go ahead. Go ahead and let's discuss the definition of Sobolev space. Actually, what is the Sobolev space? These were those the prerequisites for defining the the holder space. Basically, after we define the holder space, since this is a simpler one, then we shall switch to holder space, Sobolev space. Holder space. What is holder space? The holder space. See the notation of holder space. Notation of Hilbert space equal to this is the consist of all the function. All the function u belongs to the kth continuous functions. So it is kth derivative continuously differentiable function for which differentiation is again defined as the is in the matrix space to matrix space function. Is simply the function is u is a real valued function, real valued function. Again the notation. In this earlier lecture, we have already discussed this notation. This notation is Laplacian plus del t. This is this operator basically. We take it in great bracket. So one shouldn't be much concerned about this. This is a simple mere notation, and we have already discussed in the earlier notation lectures. So let's focus on the topic. Such that for which this is finite. This defined to be that so this whole thing should be finite. For which this is the holder space definition of holder space. Let's discuss a theorem. Since the proof is very simple, and we shall leave it as an exercise. Exercising in mathematics, giving exercise in mathematics is very common and it's very useful for students. So let's just discuss the exercise. Let's just leave the proof as exercise. The theorem. Let's come into the theorem. the space of function ck comma gamma u bar is the Banach space. Holder space is a Banach space. Probably you people should know what is the Banach space. Banach space is a complete normed space. Everyone know what is a norm space, which has defined the norm. Norm is the inner product type thing. Inner product. If a space has inner product space, then it is norm space. If it is an inner norm space, then it is an inner product space. This can be proved. Say for the norm, inner product to norm is simple. Now say this is the norm defined. Now between 2 points, this is defined as the inner product. No, basically x comma x is the inner product. Then root over taking it as the norm. For example, this is one of the norms. Many norms can be exist, and now a norm space can also be inner product. Um, so basically, this is conversion of the inner product into normed space. Now let's discuss what we were dealing with. And this complete. What is completeness? If in a set the Cauchy sequence converges, Cauchy sequence converges, then it is complete. So both the criteria, if both the criteria satisfies, then it will be a Banach space. So now focus on the theorem. The space of the CK is a Banach space. This CK, this is the Holder space, is a Banach space. Holder space is a Banach space. So now let's get ahead, and now we shall discuss the Sobolev space. Sobolev space. Let's get into the heart of this chapter. Before starting off with the Sobolev space, we shall discuss weak derivatives. This is basically weakening the notion of partial derivatives. Weakening the notion of partial derivatives. Weakening the notion of partial derivatives. Let's switch to the definition. Let's find the definition. UV. This is the space and alpha multi-index. If and only if V is the weak partial derivative, if and only if this satisfies. Basically, this won't be if and only if it is explicitly written. This is merely a notation. And provided provided integral in this whole space U minus 1 whole divided alpha for all test function phi belongs to infinitely differentiable function set on U. So this is the definition of of weak weak derivatives. If this condition is satisfied for all the test function phi, test function as in physics we use test charges and etc. But in this test function is all the this is continuous infinitely differentiable and continuous functions, and such that if this is satisfied, then d alpha phi this function is called the weak partial derivative of u. Notation. Now next. Now we are equipped with that to give the definition. Well, before that, a simple lemma shall use that would be helpful later. We calculate the derivative of u if exist is uniquely defined up to a set of measure 0. Everyone should understand what is a measure. Measure is basically it is in the real analysis measure theory. I would recommend Rodin, Rodin, read it from the book Rodin or Fulland. So if defined, then it will be uniquely defined up to a set of measure 0. That is almost everywhere uniquely defined. Now let's come into the heart of this chapter, the definition of Sobolev space. Fix 1 less than equal to p less than equal to infinity. K non-negative integer. Sobolev space WKP of U consists of locally locally summable functions. This is the open set in the open subset of Rn, and U is a real valued function for all multi-index multi-index alpha with mod alpha is less than equal to k. It should exist. Should exist. Now this weak partial derivative in the weak sense and belongs to LP. LPU. Now this LPU, all this is used very often in this measure theoretic basis of the real analysis, and it should be well understood by the well, and the reader should be well equipped with this. So that was the definition of Sobolev space. Now let us define its norm. U belongs to WKP, K comma P U. The Sobolev space. We define the norm to be norm with respect to certain space is usually denoted with the this is the two bars, and with the space in here is defined as summation mod alpha less than equal to k. Alpha is the multiset d alpha u with partial derivative to the power p dx whole to the power 1 by p, pth root, and summation alpha less than equal to ess essential supremum with respect to u d alpha u subject to the condition 1 less than equal to p less than infinity, p equal to infinity. In this last slide, we already used the condition that p should be equal, p may be equal to infinity to p may be equal to infinity, p may be equal to infinity. So this makes the two cases different. One with p less than infinity and with p equal to infinity. So this is the norm. Now take an example. U equal to B01, B01 is the open unit ball. Ux is this function defined on it for n equal to 2. This is basically this plane. This is the integrate of the set. Basically, I draw it incorrect. I have drawn it incorrect. Let me correct it. Excluding the boundary basically. So this is the B00, 1. This is for illustration purpose. Now come to the problem. Alpha greater than 0. Alpha P in. For which value of this? W1 comma PU belongs to this set. U belongs to F. This is the question. Find this. Find this. Interesting problem. Now, note that to answer this question, note that U is smooth. Away from 0. Away from 0, U is smooth. Uxi x equal to minus alpha xi x to the power alpha plus 2 x n equals to 0. Dux equal to mod alpha x to the power alpha plus 1 x n equals to 0. Phi belongs to C infinity C U fixed epsilon greater than 0. Let's continue in the next page. Okay, this page contains spaces. Now, consider this integral. This boundary U pi dx equal to minus uxi phi dx plus del p nu I ds. This isn't a vector. This is a vector which contains this nu I. This is a vector. This is a component of this vector. This is a component of this vector. Denoting the inward pointing normal. Inward pointing normal 1 del p u comma epsilon. Now, if alpha plus 1 is less than n, dux belongs to L1u. In this case, u phi nu I ds. This is a surface integral. This integral taken phi L infinity. This simple integral epsilon minus alpha ds is less than equal to c epsilon dot n minus 1 minus alpha tends to 0 for all phi belongs to c infinity u, provided alpha is less than n minus 1, alpha greater than equal to 0. Moreover, moreover dux equal to alpha plus 1 belongs to LPU if and only if alpha plus 1 is less than n. Therefore, u belongs to w1 comma p, that is, it is a Sobolev space. It belongs to the set of Sobolev space. It belongs to Sobolev space. Sobolev space is itself a set if and only if alpha is less than n minus p by p. In particular, u does not belongs to 1 comma p, u for all p greater than equal to n. This is in particular is a special case. Special case. This is our best case. This is a sufficient and necessary condition. Necessary and sufficient condition. Now we shall conclude today's lecture by simply giving a formula and without mentioning its proof. You are requested to find a proof in Wikipedia or try it yourself. For all k infinity and 1 less than p less than infinity. Introduce. Take this case to Sobolev space. WKP. WKP is the one. Again, it's a Banach space. Well, Banach space, let's recall. What's the Banach space? It is the non-linear space. Normed, complete normed space. complete norm space. What is a complete space? In which every Cauchy sequence converges. Well, that's all for today. The proof is an exercise. So thank you for watching it patiently, and goodbye.